Good morning and good afternoon. I am Serena Santi, and today I will present you my paper on the feasibility of location-based discovery and vertical handover in IEEE 802.11ah, written with Filip Lemic and Jeroen Famaey from the University of Antwerp and IMEC. As you know, there are a lot of technologies nowadays that allow Internet of Things devices to communicate with each other. On one side, low power wide area technologies such as Sigfox, LoRa, and NB-IoT offer a connectivity over a range of tens of kilometers with throughputs of at most kilobit per second. On the other side, low power short area technologies such as 802.11ah provide megabit per second of throughput, reaching shorter ranges of 1 kilometer and having better energy efficiency. Some Internet of Things use cases may benefit from the wide coverage of LP1 in combination with the high throughput and the higher energy efficiency of 802.11ah. Currently, devices being able to connect to multiple technologies were proposed, and they are called multi-radio access technologies. For example, this one is one from WCNC and allows to connect to LoRa-7 and Sigfox. As there are many technologies implemented on a device, there are also mechanisms to discover and perform handovers from a technology to another. In our work, we perform handovers to 802.11ah. However, how can we efficiently discover and connect to 802.11ah? Currently, it is energy consuming for devices to discover the availability of 802.11ah, as devices rely on periodic listening for beacons even when the technology is not available. And this is of course not desirable as we target low power performance. So, in order to avoid periodic beacon listening, we are proposing to use the device estimated location in order to know if the device is close enough to the 802.11ah network. And if the device is close, only then we start listening for beacon. Therefore, when to start listening for beacons? As I mentioned, we implemented a location-based mechanism that assumes the location of the access point to be known by the moving device and takes into account the erroneous location of the device based on the technology that is currently using. And as a result, we get the estimated signal-to-noise ratio. Then, we also configure a parameter called threshold in order to tune the policy of the mechanism based on specific use cases. In case we want more energy efficiency, then we will have a more conservative threshold, so a threshold above 0 dBm, in order to let the device connect only if in proximity of the access point. On the other hand, if the focus is on association, then it's better to have a more liberal policy, so a threshold below 0, in order to allow the device to connect as soon as possible to the 802.11ah network. In our paper, we compare location-based mechanism, that is the one on the right, to a dumb approach baseline, that is the one on the left. In the baseline, the device periodically wakes up to listen for beacons, and when the beacon is received, then the device starts the association procedure to 802.11ah. By waking up periodically, the baseline allows the device to associate whenever 802.11ah is available. However, due to the continuous idle listening, even when the technology is not available, the device consumes a lot of energy. That's why we use location estimate in order to perform the handover. And as you can see on the right side of the slide, After the device calculates the estimated SNR based on the threshold, it decides whether to wake up to listen for beacons or not. And then also in this case, if the beacon is received, then the association procedure is started. In our paper, we simulated a device moving back and forth away from a 802.11ah network, varying the threshold, so varying the mechanism policy, and the localization error. Here, we show the results for the average association time on the left and for the energy consumption on the right, both for varying values of the threshold parameter that is on the x-axis. A more liberal policy is when the threshold is below 0, and a more conservative policy is when the threshold is above 0. We compare different localization inaccuracies, as well as perfectly accurate location of the device. And we also compare different baselines based on periodic beacon listening with different periods of 1 beacon interval, 5 beacon interval, and 10 beacon interval. As you can see, baseline 5, that is the device waking up every 5 beacon intervals, is the best performing baseline, as its association time is similar to baseline 1, while consuming 5 times less energy consumption. When the threshold is more liberal, this leads to longer association time compared to the baseline 5. However, the energy consumption of the mechanism is higher. But for threshold 0, the mechanism outperforms the baseline significantly for location errors below 100 meters in terms of energy consumption, while maintaining similar association time. And we can also see that if the localization service has high localization error of 400 meters, as in Sigfox and LoRa, and the threshold policy is conservative, so the threshold is above 0, then the device becomes too conservative in making decisions, and it doesn't wake up anymore in order to listen for beacons. So we can conclude that the SNR threshold is useful to tune the association energy trade-off. Here we show the influence of localization error on the x-axis on the average association time on the left and the energy consumption for beacon listening on the right for different thresholds. We can see how low localization errors, as 10 meters, have better energy consumption and association time with liberal policy, so with a threshold below 0. If the localization error is around 200 meters, then a higher threshold is better, as the energy consumption is lower, but the association time is similar. However, as before, if the localization error is high, a higher threshold, so a more conservative mechanism, no longer allows the device to connect anymore to 802.11ah. So we can see how the choice of the threshold still makes a difference with average association time and energy consumption. But we can see still how the mechanism has good performance even in case of very large localization error with the choice of a good threshold. Here we show the influence of background noise on average association time on the left and energy consumption on the right, with different thresholds, so different mechanism policy on the x-axis. With the background noise, we are simulating a densely populated environment with devices communicated in the sub-gigahertz frequency band. And we can see when the threshold is higher than -1 dB, then the energy consumed by the device for beacon listening is 0 joule. That means that the mechanism is always correct in associated to 802.11ah. But in this graph, it's also interesting to see that when the background noise is higher, then the performance of association time and energy consumption are also improved. And this is due to possible additive noise that actually increase the coverage area of 802.11ah. And we can conclude that our mechanism has still good capacity of connection, even in case of densely populated environment communicating in the sub-gigahertz frequency band. About the conclusion and future work. So in our paper, we propose to use device location information in order to be used in a location-based mechanism. And we evaluated the average association time to 802.11ah and the energy consumption for beacon listening of this location-based mechanism, that we also compare with a baseline approach, so with a device waking up periodically as a traditional discovery mechanism. We also studied the influence of an SNR threshold parameter and the influence of location error and white background noise. I conclude that the energy consumption of our location-based mechanism is reduced by 100 times compared to traditional discovery, so compared to the baseline approach, still having the similar association time, and also the location-based mechanism has still good performances with large localization error and densely depopulated environments. As future work, we are going to study environment-specific localization error using Sumo and OpenStreetMap, and we're going to calculate the energy and delay overhead caused by localization calculation, so caused by the location service as GPS, RF, or fingerprinting. And in future, we are going to use reinforcement learning in order to adapt the propagation loss model in the mechanism. Thank you very much for your attention.